So starting to get into more calculations about percent composition, molarity. You've been balancing reactions with mass and moles being balanced on both sides. So we're just basically going to be doing a little bit more of that today. Hopefully that won't be a big shock or surprise to anyone. I figured we would do one of like each of the examples together, and then go off and work on the rest of them in groups that I'll come in and check on you, the usual thing. So percent composition, what can people tell me about what percent composition means? When I say percent composition, what is it we're actually trying to figure out?
Like the percent of a specific atom in a sample.
Okay, so would it be like how many moles of like, for instance, for ammonia, would it be the number of moles of ammonia versus the number of moles of hydrogen?
It would be like what percent is the ammonia in the, or what percent, like say if you wanted to find out the nitrogen, you would say what percent of ammonia is nitrogen, right?
In terms of what though? In terms of moles?
In terms of concentration, right?
Well, concentration, I mean, I look at that NH3, it just means that it would be 25% nitrogen and 75% hydrogen, right? Because there's one nitrogen and there's 3 hydrogens. So that's, I mean, that's fairly simple. Is that, so we don't really need a calculator for that. So is it the molar percentage?
Yes.
Okay. Anybody else have any ideas? Because I see a number of things like on the chat. I see percentage of each element. Yes, but percentage of what though? Because remember, people were able to figure these things out before they really had a good idea of like the molar concept. Like 200 years ago, people were able to figure out percent compositions of things. Right, it's mass. It's mass. So this was one of the ways that people were actually able to determine the molar mass of a lot of atoms, is by taking apart and figuring out how much mass of each atom is in a molecule, and then going backwards trying to figure out how many atoms of each one are in that molecule, and deducing what the molar mass must be. So for instance, and this is something we'll be probably be doing a little bit later, taking a substance, combusting it or burning it in the presence of a high concentration of oxygen, and then taking the mass of the carbon dioxide, the water, and anything else that might be given off, and then trying to figure out what the molar ratios must have been in the original compound. So let's just do B here, try and figure out how we would do this. So how do we start? So we've got a solution of photographic fixer, which, you know, hardly anybody uses anymore. Everyone's shooting digitally. But sodium bisulfite. So we've got 2 atoms of sodium, we've got 2 atoms of sulfur, we've got 3 atoms of oxygen. So what's the first thing we do with a problem like this to figure out what the mass composition of each atom is? What do we want to determine first? What's the first piece of information we need?
The molar mass of the fixer solution.
Yeah, we need the molar mass of the whole thing, right? So the molar mass of this whole thing, and how do we figure that out?
2 times the atomic mass number of sodium, 2 times sulfur, and 3 times oxygen.
Right, so we've got 2 atoms of sodium, we've got 2 atoms of sulfur, and we've got 3 atoms of oxygen. So notice that the question asks us to calculate the following to 4 significant digits. So that means we can't just use 23 for sodium and 32 for sulfur and 16 for oxygen. We're going to need to use as many significant digits as we can and then round to 4 at the end. So for sodium, what would be the atomic mass of sodium, looking at your periodic table? Hopefully you get your periodic table in front of you.
22.990.
Yep. So that's 2 times 22.990 grams per mole. Sulfur, 2 times, and what would we use for sulfur?
32.066.
Okay, 32.066 grams per mole. And oxygen is now 3, I know this one, 15.999 grams per mole. So when we do the math, what are we going to get for sodium? How many, what's our mass of sodium here in a mole? Because that's what we're going to assume. We're going to assume, just to make the math easier, we're going to assume we have 1 mole of that, so we don't have to do any more calculations. Just assume you have 1 mole of it.
45.98.
So that's 45.98 grams. And next one. Is Arissa the only one going to be helping out today? That's kind of sad. I mean, she's a great student. Nobody else has a periodic table in front of them or a calculator.
I got 110.1.
So you've done the whole thing.
Wait. Oh dang, hold on. I added the previous one.
All right, what's 2 times 32.066? You help me with that one.
It's 64.132.
132 grams. And the last one?
47.997.
0.997 grams. So then our total, so our molar mass of the whole thing is what? Should be around like 153 or so? 56?
158.109.
158.109? Okay. So that's our molar mass. So 158.109 is the molar mass of our fixer. So to determine the percent composition, we need to take the amount of each atom in grams and see how, as a percent, how much of the mass is sodium, how much of the mass is sulfur, how much of the mass is oxygen. So how do we do that?
So you would take, for sodium, you would take 45.98
Mm-hmm.
and divide that by 158.109.
Right. And so remember, when you have grams in the top and grams in the bottom, they cancel out. So you should have just a ratio. You should have a unitless expression, which is what we have. And then for a percentage, so that's our ratio, but we want a percent composition. So what's the last thing we need to do to that number?
Multiply it by 100.
Right, multiply it by 100. And then we just do the same thing with the sulfur, and we do the same thing with oxygen, each time dividing it by 158.109. 158.109 grams. And then multiplying by 100. So for sodium, what do we get for a percentage for sodium?
Forty point 40.56.
40.56%. Okay, so did you round the last number?
Oh wait, did you say sulfur or sodium?
Oh, I probably looked at S and said sodium. I don't know. Sodium, the first one.
That's my bad. That's sulfur then.
Oops. Okay, so that's for sulfur. So you round it to 4 digits?
Yeah.
Okay, excellent. And then for sodium?
29.08%.
0.08%. And then whatever we have left will be oxygen. So what's our oxygen?
.36% or 35.
What's the full number?
30.3569057.
Right. So we would take that 5, and since the next number is a 6, you would round that up. So you're right, 30.36%. And then hopefully when you add them all up, they'll come out to 100 or pretty close to 100. It may be, like 100.01 or 99.99 because you did some rounding. So it may not be exactly 100, but it should be pretty close. So yeah, so all of these are based on mass. And so we're going to be going backwards in some of these, and you'll be given a molecule that's like, so much percentage sulfur, so much percentage sodium, so much percentage oxygen. What is the formula? And you'll have to work backwards, taking into consideration the molar masses of each one. And when you do have a question like that, the simplest thing to do is just assume that you've got 100 grams of it. So then you can just turn these percentages into grams. So you have a bunch of stuff, and it's 40.56 grams of it is sulfur, 29.808 grams of it is sodium, and 30.36 grams of it is oxygen. And then from that, you work out the molar ratios. I don't know if is there a question like that? I don't think there is a question like that in here. Oh yes, there is, empirical formula. Here we go. So the very next one. So let's work on that one. Yeah, so classic example. So now we're given the opposite information. We're given the percent, and we need to work backwards. So here we have a compound of carbon and hydrogen. So what will we call that kind of compound? It's only got, huh?
A hydrocarbon?
Hydrocarbon, exactly. If it's only got carbon and hydrogen, that is indeed what we would call it. And so we're given the information that it is 92.3% carbon and has a molar mass of 78.1 grams per mole. Why do we need to know what the molar mass is to come up with the molecular formula?
Because they don't tell us how much hydrogen and how much carbon.
Yeah, we can figure out how much hydrogen there is without knowing the molar mass. Because it's carbon and it's a hydrocarbon. So there's only going to be carbon and hydrogen in it. So if it's 92.3% carbon, what's going to be the percent of hydrogen?
7.7.
Right. The rest of it. So there's only two things. Right. So it's 7.7% hydrogen. But why do we need to know the molar mass to get the formula, though? Anyone help me out with that? What's the molecular formula mean? Basically, what information is in the molecular formula?
Is it how many of each atom there is?
In the molecule, right? Exactly. So at the end of it, we're going to have something like, CX and HY. But why do we need to know the molar mass to figure out what X and Y are? I mean, we're going to figure out a ratio, aren't we? I mean, right now, I think we have enough information to get what the ratio of carbon to hydrogen is. What use is the molar mass?
Because it says the ratio, but the ratio is reduced, right?
When you say the ratio is reduced, what do you mean?
Like if the ratio is 2 to 1, the carbon could be 4 and the hydrogen could be 2.
Exactly. Yeah, just because we know what the ratio is, we don't know what the actual ratio is in the molecule. If it's a 2 to 1 ratio, it could also be a 4 to 2 ratio, or a 6 to 3 ratio, or an 8 to 4, or a 10 to 5. We don't know. We know what the ratio narrowed, when we simplify it, is going to be 2 to 1. But in the actual molecule, it might be 50 to 100. We don't know. So we need to know what the molar mass is to tell us exactly how many atoms of carbon and how many atoms of hydrogen go into making that particular molecule. So where are we going to start? So we got 3 pieces of information. We know the percent, and remember, this is mass percent. That's important to remember. It's not mole percent, just like we did in the last question. This is mass percent. So where do we start figuring out what the molecular formula is? What's the first thing we want to do?
Find the mass of carbon.
Okay. So we're going to want molar masses of carbon and hydrogen. So what's the molar mass of carbon?
72.0863.
Of carbon?
Of the because you would multiply 78.1 grams times 0.923, right?
Are you sure? Oh, you're working out how many grams of carbon there are. I was just asking for the molar mass of carbon.
Like on the periodic table?
Yes, exactly.
Oh. 12.011.
12.011 grams per mole. And what about hydrogen?
1.008
grams per mole. Right. So now, how do we go from a percentage to an actual mass? There's a couple of ways to approach this. So we can do it your way, and then there's the way that I do it. So you suggested multiplying, since it's 92.3% carbon, and we know that the molar mass is 78.1 grams per mole, we multiply that by 0.923, and that'll give us the number of grams of carbon in a mole of this stuff. So you already had the number. What was the number?
72.0863.
So So 72.0863 grams. So in 1 mole, we've got 72.0683 grams of carbon. So how many, how do we figure out what the mass of the hydrogen is?
You do 78.1 times 7.7.
Yeah, same number times 0.077.
Oh, right.
Because that when we add those two things up, we should get 1, right?
And then that
7.
equals
All right. So how much hydrogen do we have?
6.0137 grams.
6.0137 grams of hydrogen. So that's how many grams of carbon there are in a mole, and that's how many grams of hydrogen there are in a mole. So what's our next step? Anyone want to pitch in and help out? We want to multiply these by something. What do we want to multiply them by? Because basically what we want to do is convert grams to moles. So to do that, what do we do?
You divide it by the grams of what carbon.
Remember, I don't like to divide by anything. I like to multiply by things. That way I can cross out units. So I've got grams here, and I want to multiply by something to get me to moles.
1 mole over 12.011 grams.
There we go. Exactly. Yeah, 1 mole of carbon over 12.011 grams, and 1 mole of hydrogen over 1.008 grams. That way I can cancel grams, and I'm left with moles. So when I do that, how many moles of carbon do we have?
6.0016.
6.0016 moles of carbon. And how many moles of hydrogen?
Five, 65972.
So what is it? 5.9672,
96.
is that it?
965972.
Oh, 59. Okay. Moles of hydrogen. Now you can see that these two numbers are really close to 6, right? So because there's only 3 significant digits on the percent of carbon, and there's only 2 significant digits on the percent of hydrogen, we can feel fairly comfortable rounding these to 6. So the molecular formula would be C6H6. Now, if we didn't have the molar mass, how would we do this if we didn't have the molar mass? We wouldn't be able to get the molecular formula, would we?
Would you use 992.3 and put that as grams?
Exactly. If we didn't have the molar mass, basically we would just have to figure out what is the simplest ratio. And anyone tell me what formula that is?
Empirical formula.
Exactly, the empirical formula. So we could still figure out the empirical formula by taking this, instead of having 72.08, that's like the precise amount of carbon. We would just say we have 92.3 grams of carbon and 7.7 grams of hydrogen. And so when we did that, if we were to do that calculation and figure it out, we would find that we would have basically a ratio of 7.7 moles of carbon and 7.7 moles of hydrogen. So since we don't know what the actual ratio is, we just have to figure out what the simplest ratio is. And the simplest ratio is just 1 to 1. So the empirical formula would just be CH. And then once we got the empirical molar mass would be around 13 grams per mole. And then whenever we did get the molar mass, we would then take the molar mass and divide it by this and figure out what the actual number of moles is, because it could be C10H10 or C20H20. We don't know what it is. This tells us what the ratio is. So if you divide 78 by 13, you get 6. Okay, so it's just basically the same bit of information. So what if we were to get a final ratio of, let's say, 2.5 to 1? What will we do with that? Because we can't have 2.5 atoms in a molecule. If we had C 2.5 H1, what will we do with that formula? If this was our empirical formula, what will we change that to?
5.2.
Right, we would change it to C5H2, because we have to have whole numbers. You can't have, I mean, you can have, you can measure out half a mole of something, but you can't get half an atom in a molecule. You can't have 2.5 atoms in a molecule. You need to have 2 or you need to have 3. So it has to be a whole number. So that's exactly what we would do. Excellent. So let's move on to the next one. Now, molarity. So what does molarity mean? Anyone give me a working definition of molarity?
Molarity measures how concentrated a solution is based on the number of solute particles dissolved.
Mm-hmm. Based on the number of solute particles. So it is a measure of concentration. You're absolutely right about that. But what does this number mean? If something is 0.50 molar, what does that mean?
Is that moles per liter?
Exactly. It means that means we have 1.50 moles in 1 liter of solution. Now, it's important to remember, this doesn't mean 1 liter of solvent. So you can't take, let's say if you wanted to make a 0.50 molar solution of sodium chloride, for instance, you could not take a liter of water and add half a mole of sodium chloride to it. Why not? Why would that be the wrong way to do it?
Because it would add to its volume?
Exactly. By adding the salt to the liter of water, it's not going to be a liter anymore. It's going to increase because the sodium ions and the chloride ions are actually going to physically take up space. Not a lot of space, but they're going to physically take up space. And so the solution is going to increase in volume. So when we make a precisely calibrated concentration of solution, we would take half a mole of sodium chloride, whatever the mass of that is, and we would dissolve it in like 800 mils of water, make sure we got it all dissolved. And then we would put it in what's called a volumetric flask. So a volumetric flask, as you probably figured out, measures very precisely a volume. And so we would put it in the flask and we would keep adding water to it until the meniscus came up to a line. And that would be exactly 1.000 liters. And so we would be able to give the concentration with 4 significant digits. Okay, so that's how you really make a concentrated solution very accurately. So let's do one of these. Let's do, I don't know, let's do the third one, because there's a lot going on in that one. So I have 0.2074 grams of calcium hydroxide, or CaOH2, in 40.00 milliliters of solution. All right, so what's the first thing I need to do for this problem?
Convert grams to moles and milliliters to liters.
Right, I need to know how many moles of calcium hydroxide. I need 2 bits of information, because I want to, at the end of it, I want to have moles divided by liters. So I need to know how many moles of calcium hydroxide I have. How do we determine that? How do we convert that mass to moles?
To find the molar mass first.
Right, the molar mass of what?
The calcium hydroxide.
Right, calcium hydroxide. So how do we do that? Well, there's 2 ways. You look it up. Since we're not taking a test right now, we can just Google molar mass of calcium hydroxide. But if we were taking a test, how would we work it out?
The molar mass, the atomic mass number of calcium, which is 40.078.
40.078 grams per mole.
Plus the 2 times the atomic mass number of oxygen, which is 15.999.
Mm-hmm.
And then 2 times 1.008 hydrogen.
Grams per mole, right. And so what does that give me as a molar mass? And excellent, yeah, because you have a 2 here, you need to multiply everything inside the brackets by 2. So what's my final molar mass?
74.092.
74.092 grams per mole. All right, so I have 0.274 grams of this stuff, and I want to convert that to moles. So what am I going to do with this information? Again, I'm just doing a conversion from one unit to another. So I want to multiply by something that gives me the unit I want and gets rid of the unit I do not want. So what am I going to multiply my mass of calcium hydroxide? What am I going to use to multiply it by?
Multiply 1 mole and then 74.092 grams.
Yeah, 1 mole on top, 74.092 grams on the bottom. Grams go away. And how many moles do I have?
Zero point 0.00279.
0.00279. Keep going.
9. 2.
Okay. Because remember, there's 4 significant digits here. There's 5 significant digits here. So we want, and how many significant digits should we report for the answer for this question?
4.
4, right. There's 4 significant digits in the mass, and there's 4 significant digits in the volume. So we have to give an answer in 4 significant digits also. So that's our first part. So we've got, that's our number of moles. Now, how do we figure out our number of liters? Because that's the volume has to be expressed in liters. How are we going to do that? Somebody else want to help out here? I've got 40.00 milliliters, but I can't use milliliters because this molarity isn't moles over milliliters, it's moles over liters. So I need to change that unit to liters. What am I going to do?
You multiply it by 1 liter over 1,000 milliliters.
Exactly. That gets rid of my milliliters, which I don't want, and it leaves me with liters that I do. So how many liters is that?
0.04.
Nope. What's wrong with that answer? You're really close, but there's a problem.
You need to put liters.
No, that's fine. But this, if I just put 0.04, that would be incorrect. Why would that be incorrect?
Add to 3 more 0.
There you go. Yeah, because we need to take these are significant digits. So we need to include them. Because if we don't, if I was to put 0.04 liters in here, when I did my calculation, I would have to round it to the nearest single digit. And that's a no-no. So I want to include the other 3 zeros. So 1, 2, 3 liters. It's important to do that. Obviously, you don't have to do that for the calculation. You don't have to punch 0.04000 into your calculator. Your calculator doesn't care, but you do, because you need to remember to have 4 significant digits in your answer. So that's the reason why. So now I pretty much have everything I need to do the calculation, because I got moles and I got liters. So I'm good to go. So what's my final answer going to be?
0.06998.
0.06998. Now, remember, in any chemistry question, you cannot just give a number unless it asks you for what are the number of moles of carbon. It says determine the molarity. So remember, you always need to give some sort of unit. Grams, moles, milliliters. You got to have a unit. So here's the first part of my answer. What's the second part?
You could either put M or moles per liter.
Small m or big M?
Big.
Big, right. There's 2 answers you could give. Capital M for molar, because that means moles over liter, or you could put moles over liters. Either one is fine. But obviously big M to save time. Because we need to have put big M because there's also something called molality, which is a small m rather than a big M. And of course, if you put the 2 of them together, that means millimolar, or 1,000th of a molar. Anyone know what the small m for molality stands for? Just curious. I don't know if you've learned it. It's really close to molarity. Molality, small m, means moles of solute in a kilogram of solvent. So for water, that's really close, because 1 liter of water weighs how much? What's the mass of a liter of water?
1 kilogram.
Yeah, exactly. It weighs 1 kilogram. But like I said, when we're dealing with molarity, it's not the solvent, it's the solution. So we need to have the concentration, or we need to have the volume of the entire solution. For molality, we just need to know how much solvent there is. And so it's really, really close, but it's not exactly the same. And we calculate molality when we're figuring out things like how much does the boiling point of water increase when you dissolve salt in it? How much does the freezing point of ice decrease when you add salt to it? This is the reason why, who's lived where it's cold and there's ice on the roads? I have. Anybody else? I'm from Canada. It's really cold. Everyone else from California or something?
Yeah.
Oh man. Yeah, so in cold places, they spread salt on the roads. And salt lowers the freezing point of the ice, and so it melts. And it's dependent on how many moles of salt and the mass of the ice. So a little bit of freezing information for you guys. All right, so for each one of these, you need to have moles on top, liters on the bottom. So if you're just given a mass, you need to convert it to moles. So that's fairly straightforward for that one. Now, next question. This is if you have a concentrated solution and then you need to dilute it to a lower concentration. So here we have a solution, and that's sucrose, by the way, C12H22O11. That's sucrose sugar. So we have a sweet solution, and we need to dilute it to a lower concentration. We need to go from a concentration of 0.33 molar to 0.025 molar. So what do we do? Anyone know what formula we use to figure this out?
M1V1 equals M2V2.
So M1V1 equals M2V2. Now what does M and V stand for?
V is for volume, M is for molarity.
Right. So you could also say C1V1. C stands for concentration and molarity. So either way. So, and why does this formula work? If we were to multiply C1 by V1 and C2 by V2, what actual numbers do we get? What numbers does that give us?
The same number.
Gives us the same number, but more importantly, it gives us the same unit. What unit does it give us?
More of the sucrose.
It gives us what?
Give us the more.
Moles, exactly. It gives us the number of moles because concentration is in moles per liter. Volume is in liters. So on each side of the equation, it's going to be number of moles. That's why they're the same. So whatever the volume of the concentrated solution, the volume of the concentrated solution times the concentration of that solution is the number of moles of sucrose that are going to be in that volume. And since we're diluting it into water, the volume of the second solution times the concentration of the second solution has to be the same thing, because the only place where the moles came from were from your concentrated solution. So the concentrated solution tells you how many moles are being transferred, and that has to be the same number of moles in your diluted form. So all we need to do is just we're just basically figuring out how many moles are being transferred using the concentration of the first one times the volume of the first one, the concentration of the second one times the volume of the second one. So what's our C1 here? What's our concentration 1? Or concentration I for initial. That's another way some people put it. CI, VI equals CF, VF for initial and final. I mean, they're basically, obviously they're the same thing. So what do we put in for the first concentration?
0.33.
Yep, 0.33, no. 0.33 what?
Wait, the M.
Yeah, capital M. Always use units in your calculations. So 0.33 molar times, and what's the volume of the first one?
Wait, are we trying to find the volume of the first one or the second one?
First one.
Oh, so that would be V1.
Yeah, we don't know what it is, right? We're trying to figure it out, so we just leave it as V1. That's unknown. So, but that's going to equal the concentration of the second solution times the volume of the second solution. So what's the concentration of the second solution?
0.025 capital M.
Yep. And what's my volume of the second one?
0.025
Right, so we're gonna, no,
liters.
liters. I'm going to be a stickler for units because I'm always a stickler for units. Right, so we need to multiply by 1/1000 for the 25 mils to change it to liters. And so it's 0.025 liters. So to figure this out, we just do a little bit of moving things around. We divide both sides by 0.33 molar, 0.33 molar. So these cancel out to give me V1. Molarity cancels out, and I'm left with liters. That's the reason why you want to keep the units, because that tells you not whether or not you're setting up your calculations correctly. Because if you just have a big pile of numbers, you don't know whether you may have flipped something around, you may have put something in the wrong place. If you have units, you automatically know, okay, my molarities cancel out, I'm left with liters in the right. I don't have like 1 over liters or something like that. I've got this thing set up right. So what is the volume 1 going to be?
0.00189. 189.
189.
Or just 19.
Oh no, you're good. 189 what though?
Liters.
Liters, right. And so then we remember to go back and look and see how many significant digits should I report this number in. And there's 2 here, there's 2 here, and there's 2 here. So obviously the answer is going to be 0.0019 liters. You could also present it in milliliters if you want, by shifting the decimal place three times. So 1, 2, 3, 1.9 milliliters. Either one is fine. As long as you have the right number, as long as you have the right unit and its volumes, you need to have liters, and you need to have the right number of significant digits. So you could present it in milliliters or microliters or whatever unit you want, as long as you have the right number of significant digits. Okay. Was it the last one I was going to do? It is. All right. So work on the rest of them. I'm going to put everyone into rooms, give you guys like 45 minutes to work on them in groups. Then we'll come back and basically review the answers for them. Okay, that sound good to everybody? Everyone wants to have a Rissa in their group. She's going to help everyone out. Now, remember, I want you guys helping each other out. So if I go into the room and everyone's, got their camera off and no one's sharing anything and everyone's muted, that's really not the point of the whole thing, right? Because we could just do this at home by ourselves. So we want to be able to reach out, help each other, and get help if you need it. And I'll be in checking on everyone. So everyone found the sheet in Canvas. I just posted it this morning, so everyone has it. Does anyone need it? I can put it in the chat.
Yeah, yes, I got it.
Everyone has it? Your silence tells me you do. There's only 10 people hanging out. I'll just put you in 2 rooms then, and you can work these things out. All right. All right, there you go. I will be back in about 10 minutes to Benjamin and I'll be checking in. Okay.
Hey, Professor.
Yes.
Oh, can you make me a co-host?
Oh, duh. I keep forgetting. Yep, no problem.
And I just have a quick question.
Mm-hmm.
Is normality the next chapter, or is that not covered here?
Well, normality, molarity, basically the same thing. I don't think we've. It's a good question. I don't think we deal with it yet.
Okay, because I know it has to do with like the release of protons, so probably when we do acid-base, then. Maybe.
Yeah, and I think there is some. Actually, I need to double check. I can't remember. All right, so who give me the answer for the first one, the ammonia, NH3. How'd you figure that one out? Hello?
So for nitrogen, I got 82.24%.
82.24%. Okay, and the hydrogen? The rest, presumably.
17.76.
Does that agree with everyone else's result?
Yeah.
Sweet. Okay, excellent. What about what's this? What do we call that particular compound?
Calcium phosphate.
That's right, calcium phosphate. Excellent. So what's my percent of calcium?
$38.76.
38.76% calcium. Okay. What about phosphorus?
Oh, I thought we were just supposed to do calcium.
Oh, duh. You're absolutely right. It does say just percent of calcium ion in that. Okay, fair enough. Ask you to do more than you're supposed to. So everyone, I noticed that people worked on the asbestos problem, and everyone figured that out actually, and we looked up the actual formula for chrysotile asbestos, and I think it was given as Mg3s2 H3O8 was it something like that, wasn't it?
Yeah, you just forgot the I on SI.
Oh, I, right. Yeah, so that was the actual formula. And so, yeah, everyone got that right. It's given that empirical formula because basically it's just a repeating. It's hard to determine what a mole of that is because it's a repeating unit. So figuring out what an actual mole of it is kind of tricky. But this is the empirical formula. I think everyone got that one right. So that was excellent. So number 3 here. What was the answer we got for number of moles of calcium chloride?
I got 3.4.
So the answer was what, 3.38, I think. And then you have to round that to 3.4 because there's only 2 significant digits in each one of those measurements. 750 only has 2 significant digits in it, and so does 4.5. So whatever number you get from your calculation, you have to round it to 2. That's right. So what about this molarity for this solution here? And what is this? COCl2, what do we call that?
Cobalt chloride.
Right, cobalt chloride.
I got 0.679.
So what was the, sorry, what was the answer?
0.679 m.
679 molar or more moles per liter. Now, if I was to say calcium chloride, can I just say cobalt chloride or do I need to put a number in there? If I was writing it out.
You need a number
Right, why is that?
because cobalt doesn't have a set charge.
Because it's what kind of metal?
Transition.
Right, so you would have to put cobalt 2. It's almost always 2, but usually it's 2, but not all the time. So second one, 98 grams of phosphoric acid in a liter of solution. Oops. Ah. Why can't I just... It's not letting me... Okay. 98 grams of phosphoric acid. And that's the acid you'd find in Coca-Cola. That's why it sort of has that acidic taste, because it's phosphoric acid in there. Not good for your teeth. So what is the molarity of that? How do you determine it?
I got 1.0061, but I don't know about the Sigfrid.
All right, so 1.0061.
Or 3 zeros.
Oh, 3 zeros, 1.00061. Okay, and what's the unit? Remember, you have to have a unit.
Capital M.
Capital M, or moles per liter. So what's the molar mass of phosphoric acid?
97.994.
Okay, so it's basically, there's 1 mole in 1 liter. So the question is, what do you round this number to, right? Yeah. Have a look and see what are the number of significant digits given to you for the mass and for the volume. So first, here's the mass. How many significant digits there?
3.
3, right. And there's the volume. How many significant digits there?
3.
3. So what should we report? So here's your calculated answer, what should be the number you present as your final answer?
1.00.
Excellent, exactly. 3 significant digits as well. So you round to 3. There's your 3, 1.00 molar. Great job. All right, 2C. We got calcium hydroxide. Oh, we did that one together, didn't we? Did we do that one together? I think we did. So let's look at, so 3A, we got concentrated sulfuric acid, H2SO4. That's a strong acid. How many moles is that? So 2 liters of 18.5 molar H2SO4. That's as concentrated as sulfuric acid gets. That's definitely something you don't want to mess around with. So how many moles of sulfuric acid is that?
I got
37.
They're just 37?
Yes.
Okay.
37 moles.
Moles. Any other answers? Is that right? Just 37?
I got 9.25.
Sorry?
I got 9.25.
Okay, 9.25. So how did you get 9.25? Now again, here's where units help, because you're asked for moles and you're given 2 numbers. One, a liter, and the other, moles per liter. So what should you do with those 2 numbers to give you moles? So here we have 2.00 liters and we have 18.5 moles per liter. So what do we do with those 2 numbers if we want to get moles at the end?
Multiply.
Right, you want to multiply those 2. Gets rid of liters and you're left with moles. So when we multiply them, we do get 37, but that's not the right answer. How come? I mean, 37 is correct, but it's not the right answer to present as your final answer. What should your final answer be?
37.0.
Exactly. You need 3 significant digits. There's 3 significant digits in the volume, and there's 3 significant digits in the concentration. So your answer has to have 3 significant digits in it. So that has to have a 0.0. Because if I was grading it, I would be a mean guy and take off a point for sig figs. All right. So, and the mass. Sorry. So you've got 37 moles of H2SO4, and they want grams of it. So what's the molar mass of H2SO4?
The moles or the I like the one
Well, I
mole
know
or
how
the
many
final
moles there are.
answer?
There's 37.0 of them. I need to know what the mass of that is.
Are you asking for the final answer?
I'm just asking how you get it. I mean, what do you multiply 37 by?
Above is grams per mole.
Right. So you want the molar mass in grams over moles, because I want to cancel out my moles and I want to be left with grams. So what's the molar mass of sulfuric acid?
98.079.
0.079. Okay, so what's your final answer for the mass of H2SO4?
3,630.
3,000, how many? 3,600?
630.
630. Oh, 630?
Yeah.
Okay, grams.
Grams.
And that has 3 significant digits. Excellent. That's what you want to round it to 3. That's correct. All right. Sodium cyanide. Nasty stuff. So we've got, again, we want moles. So we're given 2 bits of information to help us with that. We've got a concentration and we've got a volume. So we get 100 mils and we have 3.8 times 10 to the minus 6 moles per liter. So what do we do with our volume? Because I can't cancel mils and liters.
Convert it to liters.
Right. Just convert it to liters. So 0.100 liters. So how many moles is that? My liters cancel.
I did a scientific notation. Can I type it?
Yeah, definitely. I would do that too. That's a lot of zeros. So that's just 3.8 times 10 to the minus 7, right? Moles?
Yeah.
Right. So what's the molar mass of sodium cyanide? It's not very high.
I got 1.9 times to the negative 5.
So what's the mass of sodium cyanide? Because you shouldn't get a lower number than the number of moles, because the mass is always going to be more than the number of moles.
Do I multiply that by 49.0076 to get
Well,
the grams?
always make sure you have your units around. So if I have moles and I want grams, remember I want to have grams on top and I want to have moles on the bottom. So for sodium cyanide, what would I put in for? So this is my molar mass here, grams per mole. So the molar mass is what, 23 plus 12 plus 15. So what is it?
I got
the total. Oh, go ahead.
58.44.
58.44. Okay, so you multiply 3.8 times 10 to the minus 7 times 58.44. And what answer do you get?
2.2 times 10 to the negative 5.
2.2 times 10 to the minus 5, what?
Grams.
Grams. Or so what was the full answer before you rounded it? I like how you rounded it to 2. That's excellent. So did you have to round up or down?
I had to round down.
Okay. Yeah, so you can see that's not a lot of sodium cyanide. That is 22 micrograms. Or microgram is 10 to the 6th, 10 to the minus 6 grams. So 22 micrograms is an incredibly small amount. So that's, yeah, cyanide is very nasty stuff. It basically attaches to your hemoglobin. The cyanide ion attaches to hemoglobin because it's almost the same size as oxygen. But whereas oxygen attaches and then comes off, and then attaches and comes off. Cyanide attaches and never comes off. So basically you suffocate. It's particularly nasty. So, ugh. So there's only one question left. So number 4. So what did you get for number 4?
0.4999 liters.
Oh, 0.4999 liters. Right, so you want to have 4 significant digits. There's 4 here, there's 4 there, and 4 there. So, excellent. Great job today, everybody. Yeah, these are fair, hopefully you'll find these are fairly straightforward ones to do. It'll get a little more complicated when we start doing acid and bases, because then you have to start considering how many moles of protons are released for every mole of acid, and how many moles of hydroxide ions are produced for every mole of base, and all that sort of thing. It gets a little more complicated, but hopefully it shouldn't be too much of a problem. Anybody have any questions before we wrap it up?
Well, for the exam, for the number 4, do we convert that to milliliters too?
It doesn't matter. If you're asked for a volume, just give a volume. Just give a number and a unit.
Okay.
If you're not told to give it in liters, or if you're not told to give it in milliliters, you're free to do it either way. Because I mean, you're given in liters, so if you give it in liters back, that's fine. But if you wanted to convert that to, was it 499.9 mils, no one's going to argue.
Okay, thank you.
Yeah.